In this video, we're going to take a look at section 3.2 on zeros of polynomials. So there are a series of ideas in this section that all kind of tie together to allow us to do a pretty big problem at the end of the section. And so we're going to go through each idea individually, talk about what it means, and then kind of build upon idea after idea until we get to the ultimate problem that's near the end. The remainder theorem states the following. If R is the remainder when the polynomial p of x is divided by x minus c, then p of c is equal to r. So it's kind of hard to make sense of what this statement is actually stating. But you have to think of c as a number, right? So there's some number here. We have x minus a number. If we take that number and plug it into the polynomial, so they're making use of the function notation here, right? We have x originally, but we're replacing x with the number c. So we're plugging that into the polynomial. The answer you get when you plug that number into the polynomial is r, which is the remainder from when that polynomial is divided by x minus that number that you're plugging into the polynomial, right? So trying to think where I should start addressing this. So for example, for this problem, we want to find, and I'm going to go back and kind of expound a little bit on the concept, but just so the idea makes sense to you, let's look at this example that we're about to do. We are given f of x equals x to the third power minus 6x squared plus 6. This is a polynomial. We are being asked to find f of negative 2. Now normally, the way I would go about doing this, so I'm going to put a normal here, if I can spell it, normally, the way we would go about getting this answer is what we learned in chapter 2, using function notation. Everywhere there's an x, we replace it with negative 2. So we're going to have f of negative 2 equals negative 2 to the third power minus 6 times negative 2 squared plus 6, and then we would just simplify and we would have our answer, right? This is going to give me negative 8 minus 6 times negative 2 squared is positive 4 plus 6. And when you work that out, you get negative 26. So I'll kind of leave the rest of the details there to you. But you get f of negative 2. Let's try that again. I don't like the way the f turned out there. F of negative 2 equals negative 26. And that's the right answer. And if you type negative 26 here into this box, it's going to be correct. But you're not doing the problem the way you were supposed to do it, but MathXL is not going to know. Right? My math lab, whatever we're using, isn't going to know how you got the answer. It's just going to know it's the right answer. But what the remainder theorem is telling us, and this is the way we're supposed to try to do this problem, and you want to do it this other way, this alternative way, not because it's not a new, how do I want to say this? Like if I'm given this problem in a vacuum, like I'm not given any context and I'm asked to find f of negative 2, this is how I'm still going to do it. Even though I know there's another way to have arrived at the answer, this is still the way I do these problems. So what we're about to do isn't necessarily going to change the way you do these kind of problems in the future, but we're trying to practice a concept now so that the problems we're going to be looking at later will be, doable. So because what we're about to do is going to require doing some division, and we're going to need the information from that division for other things, not just for evaluating what the polynomial is equal to, but we need other information from that division. And it's just actually a pretty quick way of evaluating a polynomial. And given what we're about to be doing, this is going to be the way we want to, handle the situation. So I know it's really cryptic. I'm sorry, maybe I shouldn't talk about what we're about to do with so little detail, but just take my word for it now. Practice doing it this other way, which is, let me explain what that is. So the remainder theorem tells me I have another way of figuring out what this answer should be. It's the remainder. That's what R is in the remainder theorem. It's the remainder when the polynomial, which in this case we're calling f of x, but in the remainder theorem we call it p of x. Sorry, that parentheses is bugging me a little bit. when f of x is divided by x minus the number we are plugging into the function to begin with, the -2 in this case. So x minus -2, which of course is normally written as x plus 2. All right, so we want to divide by x plus 2. We want to divide that into f of x. And whatever remainder we get from that division should be the answer to this question. It should be -26. So we're going to do the problem this way, and we can confirm that the remainder we get matches the answer we are expecting to get, which is -26. Now to divide, right, f of x is x to the third power minus 6x squared plus 6. We want to divide this by x plus 2. And one way to go about doing that is using long division. So I guess let me just scroll over this way. We take the divisor, right? So this is called the divisor. This is called the dividend. So when we're dividing, the thing we're dividing into is called the dividend. The thing we're dividing by is called the divisor. And to divide these, one way you could go about doing this is using long division. So you put the divisor on the outside over here, so we'd have x plus 2 right here. The dividend goes on the inside of this contraption, so we have x to the third power minus 6x squared. We're going to leave a space because the next term should be x to the first power, right? If we're going in descending order, the next term we would expect is x to the first power. We don't have one in our dividend, so we leave that space open and we put the plus 6 on the end, right? Or, you know, I don't like doing this, but this is a common approach that a lot of students prefer, is to put a plus 0x. I just like to leave it as an empty space, but you could also put 0 there as a placeholder. So whatever you'd like to do is fine. Now to divide, and so let me preface what I'm about to do with this. We actually have a shortcut way of dividing these that we're going to use instead. But I do want to review long division, and maybe this is a little preemptive of me, I might be doing this a little too early, but we will need long division for 3.5. And so I'm kind of reviewing it now, and then when we see it in 3.5, I'll probably review it again in that video too, but the idea is I'm kind of going over it now so that when we see it again in a couple more sections, you'll hopefully remember how to do it. And it's not that we'll have to do this very often, but there's a few problems in 3.5 where we have to do this long division. So I kind of want to prime you for that now. So the way we do long division is we ask ourselves, what do we multiply to the first term here, which is x, to match the first term here, which is x to the third power? What do I multiply to x to get x to the third power? The answer is just x squared, right? X squared times x gives me x to the third power. So you answer that question, whatever the answer is, you put up here at the top. This is where your quotient's going to show up. And then you multiply it. You multiply this to your divisor. But the thing is, there's two terms in your divisor, so you have to distribute it to both of them. X squared times x gives me x to the third power. X squared times 2 gives me 2x squared. Sorry. Okay, let's try that again. Okay. Then, just like you do with long division of numbers, you subtract. So I'm going to subtract this from what's above it to see what's left over that I still need to manage. Because there's two terms, when I go to subtract, it has to be distributed. So I'm going to distribute that minus sign to both terms. And then you combine like terms. And what should always happen when you're dividing polynomials, if this doesn't happen, you are just spinning your wheels and you're not actually progressing to the answer appropriately. The highest power of x should cancel out. If the highest power of x is not canceling out, you're not getting anywhere, right? So x to the third powers both cancel out. We combine these together, we get negative 8x squared, right? You bring the next term down, and this is why it's nice to have something actually here as a placeholder. You bring down the next term, which is the plus 0x. Usually I leave this blank, and I just think of it as I bring the blank down. So this will just stay blank. It's just not there. But if you're having the placeholder there, you bring that down, and then you just repeat the process. So, you know, some students really struggle with long division, but really it's an algorithm with the same steps repeated over and over and over. So once you learn the set of steps, you just apply those same set of steps repeatedly. So once you figure it out, it's not too bad, right? What do I multiply to x to get negative 8x squared? Now I want to match this completely, so I want to match the negative and the 8 and the x squared. What do I multiply to x to get negative 8x squared? You multiply by negative 8x, right? Negative 8x times x gives me negative 8x squared. Negative 8x times 2, because we have to distribute it, we multiply it to the 2, we get negative 16x. All right. Then we subtract, which means we distribute a negative sign through this. Negative of negative 8x squared makes that positive. Negative 16x squared, when I take the negative of that, makes it positive as well. Combined like terms, the highest power of x cancels out. That has to happen every time. And then we combine these together. 0x plus 16x is still just 16x. So really the 16x just gets copied down because 0 does nothing to it. It doesn't change it at all. Then you bring down the next term, which is the plus 6, and we repeat the process one last time. What do I multiply to x to get 16x? Let me just move it over here. Okay. And we're going to multiply by 16. So we'll put plus 16 here. 16 times x gives me 16x, so these perfectly match. 16 times 2 gives me 32, positive 32. And don't forget, I get students that do this the first time and then they forget on every step after it. You have to subtract, which means you distribute a negative, which means both of these change sign. That's what most people remember is change the sign of both of those terms. Whatever they are, switch it to the opposite. That's how you subtract it. The highest power of x cancels out, and we get negative 26. Well, you should recognize that as the answer we were looking for, because that's the remainder. So the remainder theorem tells me that f of negative 2 equals the remainder. So whatever I get for the remainder, that's the answer I was looking for this problem. And so we confirm the remainder theorem works, right? We did it the normal way. We got negative 26 as the answer. We tried it by division. Our remainder was negative 26. That's the answer, right? And just to kind of diagram everything, so this is the remainder. This up here, which we're not really using for this problem, but it's going to become relevant for some other things we're about to do, this is called the quotient. It's really the answer from your division, right? So, with our division problem, we have a dividend, we have a divisor, we have a quotient, we have a remainder. Well, now, again, there's two things I want to do at this point. I don't know which one to do first. I want to show you the shortcut. So this was doing this by long division, and you can see it's a pretty long, tedious process, full of plenty of places to make a mistake, right? It's fraught with danger. There is a shortcut way to divide in this particular instance that would save us from making mistakes. You know, it makes it less likely for us to make mistakes, and it's a lot faster, and we get the same information. And it's called synthetic division. So maybe I'll go ahead and show you the shortcut first, and then I'm going to jump back to the remainder theorem to explain why it works. Why would the remainder be the answer we're looking for? Why is that happening? All right, so the shortcut way of dividing this is called synthetic division. So I'll do that maybe right here. And you'll see we'll get the same stuff we're getting over here, but in a more compact form, and we're going to get it more quickly. Is that how you would say that? So synthetic division works by setting up this kind of a contraption. And then, so from the remainder theorem itself, we have this expression x minus c, right? X minus c. That's what we're dividing by. And that is the only time you can use synthetic division, is if you're dividing by something of the form x minus c, which just so happens to be exactly the thing that we're dividing by in this entire section. So every time we're doing a division, we're dividing by something of the form x minus c, which means every time we can use synthetic division in this section. C in this case is equal to negative 2, right? So if you go back to this form, the minus sign's right here. C is what comes after the minus sign, which is the negative 2. Right? If you look at it in the usual writing, x plus 2, it's going to be one of those cases again where C is the opposite sign of that number in the expression, right? We have plus 2 here. That means C is going to equal negative 2, right? So this is the value for C. Oh, I just cannot draw arrows here. C, and that's what we want to put outside the box at the top. So we have to identify what is C equal to, and then put that number outside the box at the top. Across the inside of the box, we want the dividend. But what we want is the dividend without any variables, right? We want to take the variables out and just focus on the numbers themselves, right? So I'm going to write the dividend across the top here, but just the coefficients of the dividend. So here's my dividend right here. You can still see it on the screen. You start, and the rule is it has to be from highest to lowest power. As long as you write it from highest to lowest power, this method will do the division for you, in a shortcut manner. I don't know. I'm trying to think of how to describe it. The way I said the sentence, I didn't really set myself up very well to say the rest of what I wanted to say. And I'm sorry, I keep making commentary on my own, teaching. I shouldn't do that. I should just teach and not make commentary on it. All right, highest to lowest power, coefficients only. Leave the variable part out. That's what makes this process quicker. Right, so we'll start with the highest power, which is x to the third power. The coefficient here is a 1. It's invisible, but it's a 1. So we're going to put 1 here. Just 1, not x to the third power. Then we go to the next highest power of x, which is x squared. The coefficient there is -6, so we just put -6 here. And here's where you got to be careful. Because, of course, here I actually wrote it in, but in the problem you wouldn't see a 0x here. But when you're doing synthetic division, it has to go from highest to lowest power. And every power of x has to be accounted for starting from the highest power. So if the first number is x to the third power, the next one has to be x squared. The next one has to be x to the first power. And if it's not in your dividend, you have to put a 0 as a placeholder. So here I could have just left this space blank and everything would still work out fine. But in synthetic division, you have to put a 0 in as a placeholder there if you're missing that power of x. And then the constant term goes last. And so we get 6 again. All right. Now, here's how the process works. You drop the first number below the box, and I like to put an arrow there to occupy that space because actually nothing should go here. But if you leave it blank, I find some students actually write a number in that space, and a number should never go here. So by drawing in an arrow, it occupies that space, and we're not tempted to put something else there that doesn't belong there. Drop the 1 below the box. Then you take whatever number you currently have below the box, multiplied to c, right? So this is, I should put c right here. This is c. We take this number multiplied to c. So we're going to multiply here. And this is going to look messy the first time I do it because I'm like adding in commentary on my work. So you can kind of see what the thought process is. But when you don't have to write all these arrows and all this wording in, it's a very quick process. You can get very quick at doing this. 1 times -2. Whatever you get when you multiply, you write it underneath the next number inside the box. So whatever that's equal to is going to go here. 1 times -2 is going to be -2. So I write the result underneath the next number inside the box. Then you add that column together. -6 plus -2 gives me -8. Notice I had a -8 here, right? -6, -2, -8. So we're doing the same math that we're doing in the long division, but we're doing it without having to think about like terms or the variables, right? The numbers just line up where they need to be to give us the result that we're supposed to get, right? Repeat that process. -8 times -2 is +16. Write the result underneath the next number inside the box. So we're going to write 16 here. Add that column together. 0 plus 16 is still 16. Again, notice that's exactly what we did over here. 0 plus 16 gave me 16. Multiply. 16 times -2 is -32. Write the result underneath the next number inside the box. Add that column together. 6 plus -32 is -26. And so you should be able to recognize what all these numbers mean, right? -26, the last number we're getting in the synthetic division, that's the remainder. And again, that's the answer we were looking for, right? That's the remainder. That leads me to this result here. The numbers in front of the remainder are your quotient, but the variables are missing. So it's off screen right now, but let me scroll up a little bit so you can see. This was my quotient. That's, look at the coefficients here. 1, -8, 16, 1, -8, 16. This is your quotient, but the variables are missing, right? We took the variables out of the problem to start. The variables are missing here, so to finish the problem, we have to put the variables back in to the answer. And so it goes from highest to lowest power. ending on the constant term, right? So 16 will be the constant term. -8 will be the coefficient of x. 1 will be the coefficient of x squared, so it's 1x squared. And that's how you get your quotient back out of that contraption, right? You put the variables back in with those numbers. You just go from highest to lowest power. I like to start from the last number and say that's the constant, that's x squared. But I've heard students tell me what they prefer to do is think of this as you start with one less power in your quotient than what you had as your highest power in your dividend, right? So our dividend was x to the third power. That means our quotient will start with x to the second power. You just go one power less to start with on your quotient. All right. So that's synthetic division. That's a shortcut. So I know that's one example we've done so far, and we're already 20 minutes into the video, which actually isn't too bad. But I just wanted to, there's a lot of stuff to explain to kind of set the groundwork for moving forward. All right. Now, briefly, I want to go back to the remainder theorem because this is something I like to do. I like to explain it to the extent that I am able to. Now, there are some topics that we cover where even I'm a little fuzzy on like how that actually works mathematically, and I usually just don't bother to talk about it. But when I do understand it, I like to share that knowledge. And I feel that if by sharing that, it helps other students understand, they'll do better with the material, right? Because if you understand something, you're better able to remember it. You're better able to execute the process or whatever it might be if you understand why things are behaving the way they're behaving. So understanding is the best thing for learning if you can get to the understanding. Memorization's like one level of learning. There's the whole, if you take like education classes, they have this whole, I can't remember the name of it now actually, which maybe I should, and that's an embarrassment on my part, but there's different levels of learning, and rote memorization sort of the bottom level, and then I can't remember what the other levels are. Bloom's taxonomy, that's what it's called, I think. So, and they kind of categorize it into these different areas, and like I want to say the top area is like understanding it, right? Being able to understand it and teach it to other people. That's kind of where you want to get, but it takes a long time to get there. Even for me, having, been a student, earned my degree, even when I had earned my degree, I don't think I really understood a lot of the stuff that I did as a student, right? You don't really understand it. You just kind of get through it somehow in whatever way you possibly can. And I think only after I started teaching did I really start to fully understand some of these topics, right? So it's years of mastery to really understand. But anyways, not years of mastery, but just years of work to try to master it. And I still don't feel like I have mastery of this content. I think there's other people that have much deeper understanding of this stuff than I do, right? But I try. So anyways, I'm digressing, getting philosophical. Don't need to be doing that. So here's why the remainder theorem works. It's based on the formula that accompanies every division problem. So anytime you're dividing, it always starts off as a dividend being divided by a divisor. And that division can be represented as a fraction. This is a division. Dividend over divisor means we're dividing these two things. Every division problem starts off that way. If it's a division problem, this is what's going on. And then every division problem ends with a quotient that we get from the division. And not occasionally, oftentimes, there will be a remainder. So a part that's left over that didn't quite, if it doesn't divide evenly, there's going to be a little bit left over at the end. That's called the remainder. And the thing about the remainder is it's still getting divided by the divisor. Right? So I can remember, I think everybody remembers this in elementary school, when you're first learning division, and you get a remainder, you put R, whatever the remainder is, in your answer, right? So if you're dividing these numbers and you get a remainder of 5, you put R5 next to your quotient. And that's really bad form. And I kind of wonder what's the rationale for doing that? Because I think the proper thing to do isn't asking too much of students. That remainder is still getting divided by the divisor. It never made it out of the division. So the proper thing to do with that remainder is to add it to the quotient, like we're doing here, still getting divided by whatever that divisor is. So it's going to be a fraction, right? The remainder is 5. It's still getting divided by whatever thing you were dividing by at the beginning. All right, so that's how every division problem goes. It starts off like this, and it ends in this form. Now, what we can do with that formula, this is actually, it's amazing what division actually makes possible. So we can rearrange this formula, right, by getting rid of the fractions. And we can do that by multiplying the common denominator to both sides, right, which is whatever the divisor is. I don't know. Again, we're talking about these ideas very abstractly. I don't have a specific idea of what the divisor is. I don't know if it's a number, if it's a polynomial. It doesn't matter. Whatever that divisor is, that's the common denominator in this formula. So we will multiply it to both sides. Multiply the divisor to the left-hand side. Multiply the divisor to the right-hand side. And on the left-hand side, there's nothing else going on here. There's nothing complicated going on. Think of it as being over 1. The divisors cancel out, and we just get dividend. Right? We just get the dividend by itself on the left-hand side. On the right-hand side, it's a little more complicated. You have to distribute it, and even though this is not a fraction, you have to multiply it to that, and you have to multiply it to this. So you're going to have the divisor being multiplied to the quotient, whatever those happen to be, they're multiplied together, plus when this gets multiplied to the second term, it's a fraction, and the divisors are going to cancel each other out, and we'll just have the remainder left over. So it'll be plus remainder. So this becomes the formula for that division scenario. And again, this formula also applies to every division problem. One use of this formula would be to check your answer. So if you wanted to know if you got the right quotient and remainder, what should be true is if you take the quotient times the divisor and then add the remainder to that result, it should add back up to the dividend. If it doesn't, you don't have the right answer. So you could use this to check your answer. But you can also use this to prove the remainder theorem that we just talked about. So the remainder theorem says if R is the remainder, so we want to use capital R for the remainder, so we'll substitute that. The remainder, we're going to call that capital R. When the polynomial p of x is divided by x minus c, that makes p of x the dividend, and that makes x minus c the divisor, right? The thing we're dividing by is the divisor. The thing we're dividing into is the dividend. And I usually ask students to help me identify which one's which, and they kind of sit there quiet. When I have a full class, I'll ask that question. Usually somebody will eventually answer, and sometimes I just guess. I kind of put my students in that circumstance of, if nobody's saying anything, I just sit there and wait. And so somebody will just guess, and they don't care if they're right or wrong. They just want to get things moving. So I think that happens sometimes. But a lot of times I'll have a student who knows. They can tell. So plug those in, substitute those into this formula. The dividend is p of x equals, the divisor is x minus c. Now, what is not referenced anywhere in the remainder theorem is the quotient, because it really doesn't matter what it is. And so we don't have anything to substitute in for that, so we'll just keep calling it quotient. But so the description they're giving in the remainder theorem leads to this scenario right here for our division, right? They're talking about dividing, so this formula can be applied. And the division they're referencing, the division they've set up, gives us this. P of x for the dividend, x minus c for the divisor, and r for the remainder. Now, the conclusion is that P of c is equal to r. So if I take this formula, I'm sorry, I didn't really plan out the real estate on the screen for this problem very well. So I'm going to do it down here, even though it's a little bit disjointed. So let's go down here. We want to find P of c, right? That's what the conclusion is interested in. What is P of c equal to? So if I don't know what the polynomial is, but I do have this kind of little formula here for that polynomial, right? P of x is equal to x minus c times the quotient from that division plus the remainder from that division. Right? This is all I have to go on based on the description that they've given me. And so let's take this equation, this formula that I have, and plug c in for x. So I'm taking x, replacing it with c. Do the same thing on the right-hand side of the formula. So instead of this x here, we're going to have c minus c times the quotient plus the remainder, which we're calling r. Right? Now, we're getting c minus c when we do that, which is 0. 0 times the quotient plus the remainder, right? But 0 times the quotient is still 0. So we get 0 plus r, and this one's kind of funny because I'll say, this is going to be 0. 0 times the quotient is 0. 0 plus r is what? I'll ask my class that, and they'll say 0 because everything's been 0 so far. But 0 plus r is r, right? It's going to be r. And so we just proved the remainder theorem, right? This is a proof that this remainder theorem is true, right? And that's why it works, because when you plug in c for x, it wipes out this first term of this division formula, and the only thing left is the remainder. So p of c would have to equal the remainder. So that's why it works. Okay, so that's the remainder theorem. And there's going to be a couple problems on the homework where that's all you look at is the remainder theorem. So like I said, it kind of looks at one idea separately. It takes, how do I want to say this? You consider each idea individually and do a few problems on each idea separately. But then we're going to be building on those ideas to a more complex concept. All right. So we're moving on to the next concept. Now, before we can tell you the next theorem, we have to define a term here. And it's kind of a weird label that we give numbers, but if p of c is equal to 0, right, then c is called a 0 of the polynomial p of x. So remember, c is a number. And if plugging that number into the polynomial makes it equal 0, then we call that number a 0 of the polynomial. I'm not saying c is equal to 0. I'm just giving it this label of 0 because of what it does when it's plugged into that polynomial, right? So if, p of 5 is equal to 0, then what I would say is 5 is a 0 of that polynomial of p of x. Now, oftentimes I won't say of this polynomial. I'll just say 5 is a 0, and it's implied that I'm referring to the polynomial in the problem that it's a 0 of. So we have to be specific. It's a 0 of what, right? And what that means is 5 makes the polynomial equal 0 when I plug it in. That's all 0 means. It's what it does when it gets plugged into the polynomial. All right. And you'll notice that that's what this section is about, right? In this section, ultimately what we're trying to accomplish is being able to find zeros of polynomials. I want to be able to find all the numbers that make a polynomial equal 0. That's my goal ultimately in this section. And we're slowly getting to that, maybe a little too slowly, so I'll try to pick up the pace here. All right, so here's the next concept. Factor theorem. X minus c is a factor of the polynomial p of x if and only if c is a 0 of the polynomial p of x. All right, so x minus c is a factor, so that's the phrasing here of a polynomial. And we have c as a 0 of that same polynomial. And we're using the connection here of if and only if. Now, if you go up through the hierarchy of mathematics, you do college algebra, you do trigonometry, calculus, differential equations, linear algebra, and you go beyond that, you might say, what other math is there? What do you end up doing in math after you reach that level? You do a lot of proofs. That's a lot of what math becomes at the higher levels. And in doing proofs, you try to prove things like this theorem, And you'll see the phrase if and only if. I learned that phrase fairly late in the sequence of math classes that I took, right? It's not something that you really, maybe it was introduced to me like I'm introducing it to you now, but if you only see it once, you might not remember it, right? But I can remember having to learn what that means because we would have to prove statements with if and only if. And it's more difficult to prove. It's actually, having that phrase there means there's two things you have to prove. You have to prove that if x minus c is a factor, then c is a 0. And you have to prove the reverse. If c is a 0, then x minus c is a factor. So if and only if means that it works in both directions. If x minus c is a factor, then c is a 0. And also, if c is a 0, x minus c is a factor. And you have to prove both of those things are true if you want to prove this statement. Essentially, if you have one, the other one's automatically true, right? If x minus c is a factor, then we know that means c, that number c, is a 0 of the polynomial. And if c is a 0 of the polynomial, if we're given that information, then we can conclude that x minus c is a factor. So if one is given to us, we know the other one's automatically true. And we might kind of be using both directions in this section, right? So if we find that x minus c is a factor, we can use that information to conclude that c is a 0. But we could also be told, hey, c is a 0 of this polynomial, and from that, in fact, we actually will be doing this in the next section, 3.3, they'll tell us this number is a 0 of the polynomial, and from that we can conclude that x minus that number would have to be a factor. All right, now, I'm not going to prove both directions here, but I just want to, talk about why this might be true by going back to the division formula. Do I need to do that here? I'm trying to think. So, trying to remember how I do. I don't know. I'm drawing a blank all of a sudden for some reason. Like, how do I address this? So, let's start with this. Yeah, I think this is the way I do it. Well, because one direction is kind of obvious. If x minus c is a factor, then your polynomial is going to look like this. Right? I guess I am going to prove both directions here. X minus c would be a factor, and then you would have some other factors, right? So other factors. Right. So if you look at all the factors of p of x, if x minus c is a factor, then it would have to be one of the factors, and then you would have some other factors, but they don't really matter, right? And then if we plug in c for x, again, the same thing happens that we saw in the division formula. We'll have c minus c times some other factors that are in this problem, but that's going to be 0, and then 0 times whatever I get from this is still going to be 0. And so I get p of c is equal to 0, which means that c is a 0 of the polynomial. Right? So that proves one direction. If x minus c is a factor, then c would make the polynomial equal 0, which means, by definition, c is a 0 of the polynomial. Right? So this is if x minus c is a factor, then we would have this, then we get this conclusion, right? Then c is a 0. The other direction is a little more difficult to prove, and I think that's the one I normally focus on. If c is a 0, let's start with that assumption. If c is a 0. And the reason I like to do this one is because it utilizes the remainder theorem that we just talked about. If c is a 0, what does that tell me? That tells me that if I plug c into the polynomial, the answer I would get is 0, right? That's the definition. If c is a 0, it's a number that when I plug it in makes the polynomial equal 0. But we just learned in the remainder theorem that this would be the remainder when the polynomial p of x is divided by x minus c. Right? And so if I go back to my division formula again, I can prove this statement to be true, right? The dividend equals the divisor times the quotient, and again, the quotient doesn't matter in this problem, it's not referenced at all, plus the remainder. Right, that's my division formula. That's true for every division, and I'm considering that because we're talking about a division right here. P of x is still the dividend, right? So I'd have P of x here. The divisor is x minus c. The quotient, we don't know. We haven't referenced it, so I'll just keep calling it quotient. And the remainder is 0, right? If c is a 0 of the polynomial, then the remainder must be 0 from that division. And so I'm going to plug in 0 for the remainder. But if that's equal to 0, it just goes away, right? And so what do I end up with? I end up with P of x equals x minus c times the quotient. And the plus 0 part just goes away, which means I have x minus c as a factor. And the other factor, and this is kind of an important detail, from this division, the other factor is the quotient from that division. And we will need to use that for some of these problems, right? So if we identify c as a 0, we can use that to factor our polynomial. X minus c would be one of our factors according to the factor theorem, but the other factor is going to be the quotient from that division when x minus c is divided into the polynomial. And so we get this conclusion here. Right? So that proves the factor theorem, right? By going through this logic. If c is a 0, that means the remainder is 0 from that division. If I plug in 0 for the remainder, that part goes away. We just have the divisor times the quotient. But the divisor is x minus c. And it's factored now, because what factored means is you have only things being multiplied together. And that's what we have here, right? With the remainder out of the picture. Now, if the remainder is still there, this isn't factored because you have two terms. You have this plus this. You have two terms. That's not factored. But with the remainder being 0, it disappears. You end up with just two things being multiplied together, so they are factors now. Two things being multiplied means you factored. And so x minus c is one of those factors. The quotient would be the other one. All right, so let's take a look at an example. Determine whether the given binomial is a factor of the polynomial following it. If it is a factor, then factor the polynomial completely. All right, so we want to know if x plus 4 is a factor of x to the third power plus 6x squared minus 7x minus 60. If it is a factor, then we want to go ahead and factor that polynomial. Now you might say, oh, factoring, I've done that before. Why don't I just factor this one like I've done before? So unless you already know this material, this is something that you could not factor previously. This cannot be factored by finding two numbers that multiply to 60 and add to whatever something else is. Right? That only works if it's a trinomial, and this is not a trinomial. There's 4 terms. In fact, the only method that you might possibly get away with using here that you've learned previously is factor by grouping. But factor by grouping doesn't work here either. So all of the methods that we've talked about previously in this course will not work to factor this particular polynomial. The only way we're going to be able to factor it is to use the concepts that we're learning in this video. And that is using division, using the factor theorem. We can try to factor this down. The factor theorem tells me that x plus 4 will be a factor if negative 4, so how do I want to say this? If c, so this is the idea I'm using. Let's redo this. X minus c is a factor if c is a 0. Right? That's what the factor theorem just told us. Right? So I can say, yes, this is a factor if c is a 0. Now, what is c equal to in this case? Remember, we're comparing it to x minus c. Oh, it's really hard to see there. We're comparing this to x minus c. And so c is the opposite sign of this number that we have in the expression. It's a plus 4, which means c is negative 4. So if negative 4 is a 0, so I want to put if here. If negative 4 is a 0 of the polynomial, then yes, x plus 4 will be a factor. How do I determine if negative 4 is a 0 of this polynomial? What I'm asking is, if I were to plug negative 4 into this polynomial, would it make it equal 0? So one way to check would be to take negative 4, plug it into that polynomial, and see if you get 0. If you do, the answer is yes. Negative 4 is a 0, which means that x plus 4 would be a factor. Right? So you see how all the ideas are connecting here. If you don't get 0, then the answer is no. Negative 4 is not a 0, which means x plus 4 would not be a factor. That'd be one way to check, but here's the problem with that. If it turns out to be a factor, if the answer is yes, then we're supposed to factor this polynomial. But we won't be able to do that if the way you're checking is just plugging the number in. The only way you're able to factor, remember from the factor theorem, we saw this when we proved it, is that x plus 4 will be one of the factors, but then the quotient from a division is the other factor, which means we're going to have that division accomplished in order to be able to factor this polynomial like we're supposed to. And so if we're going to have to do a division anyways, we might as well use division to check to see if negative 4 is a 0, right? So negative 4 being a 0 means it would make this equal to 0, which would be the remainder that we should get when we divide these two, right? If the remainder is 0 when I divide these two, that means negative 4 makes the polynomial equal 0, which means that negative 4 is a 0 of the polynomial, which means that x plus 4 is a factor, right? So that's how the remainder theorem connects in with the factor theorem. So we want to do a division. This is my value of c, right? C is equal to negative 4 in this problem. So we'll use that in our synthetic division. The dividend goes across the top. Almost said the quotient. The dividend goes across the top. Just the coefficients. That's, I think, what I was kind of getting confused there. 1, 6, negative 7, and negative 60. Right. We go through the synthetic division. So this time I'm not going to put any commentary. We're just going to go through the process. Drop the 1 below the box. 1 times negative 4 is negative 4. Add these together, you get 2. 2 times negative 4 is negative 8. Add these together, you get negative 15. Negative 15 times negative 4 is 60. Add these together, you get 0. The remainder is 0, which tells me that my arrows are horrible. I want to do a double arrow thing there, so let's try that one more time. This tells me that negative 4 is a 0 of the polynomial. Right. So if the remainder is 0, that means this number, when it's plugged into the polynomial, is going to make the polynomial equal 0. That, by definition, means negative 4 is a 0 of that polynomial. And according to the factor theorem, if negative 4 is a 0 of the polynomial, x minus that number, x minus negative 4, which is going to be x plus 4, x plus 4 is a factor. And so the answer is yes, x plus 4 is a factor of that polynomial. All right, so that's the way we want to check. You're going to take your polynomials and divide using synthetic division. And if the remainder is 0, the answer is yes, it's a factor. If the remainder is not 0, the answer is no. So that's really the simplest way I could break it down. Now again, I'm trying to add in context there to explain how the ideas are working, but if you just want a simple, direct explanation of what you're supposed to do here, that's it. Divide those polynomials using synthetic division. If the remainder is 0, the answer is yes. If the remainder is not 0, the answer is no. Now, because the answer is yes, we're told to do some more work. We're told if it is a factor, then you have to factor the polynomial completely. And so we have the original polynomial, x to the third power, plus 6x squared, minus 7x minus 60, and we want to factor this. Right? I'm sorry, I get and when I use the smartboard in my classroom, it's just easier, and so I guess I think about how it looks on that, and then when I'm actually doing it with my setup at home, I get a little frustrated when it doesn't look quite as nice. So I apologize for that. Okay, so this can be factored now. So x plus 4 is one of the factors, so that'll be one of my factors here, x plus 4. And as I mentioned, the quotient from that division will be your other factor. So without this division, you're not going, I was about to go into my southern dialect. I'm actually from Florida, so I, sometimes we'll have a southern, I'll say y'all or things like that, but and I can't remember what I was just saying now, but the quotient will be the other factor. So without this division, you wouldn't know how to factor this. You need this division in order to factor this polynomial. All right. And so we have to put the variables back into this result, right? We can't just put 1, 2, negative 15. It's 1x squared, right? Plus 2x minus 15. And so now we have just factored this polynomial that would not have been factorable with any of the other techniques that we have gone over previously, right? And so it's a pretty interesting, it's a pretty neat thing that you're able to do with this factor theorem. But it's all contingent on being able to find a 0 of the polynomial. You have to find a 0 first in order for the factoring to be possible. Now we're not done factoring, because now that we have this down to x squared, the previous methods that we have talked about in the class will work for factoring it further, right? So once you get it down to a quadratic expression, those are things that we've learned how to factor with other techniques, easier techniques than what we're doing now, right? So this one we can factor by, and I say easier, but maybe not. You might disagree. You might think this is easier than what we did before. But this one we can factor by finding two numbers that multiply to negative 15 and add to positive 2. That's going to be positive 5 and negative 3. Positive 5 and negative 3 multiply to negative 15. They add to give me positive 2. So that's how that one will factor. And then the x plus 4 is still a factor, so we copy that down. And so we just factored this polynomial. And by having these factors, we can identify more zeros of the polynomial, because remember, the factor theorem works in both directions, right? If negative 4 is a 0, then x plus 4 is a factor. But it also works the other way around. If x plus 4 is a factor, negative 4 is a 0. And that applies to these other two factors as well. If x plus 5 is a factor, then negative 5 is a 0. If x minus 3 is a factor, then 3 is a 0 of the polynomial. So this gives us some other zeros for that polynomial, which again is ultimately what we want to be able to identify. So the problems we're about to get to here in just a few minutes we are trying to find all the zeros. So once you get everything factored, then you can identify what all the zeros are from the factors, right? -4 is a 0, -5 is a 0, 3 is a 0. These would be all the zeros to that polynomial. It wasn't asking for that, but I just want to point that out. All right, let's move on to the next example. Okay, so in this problem, we're being asked to determine if -2 is a 0 of the polynomial function following it. Again, on this one, you could just take the number and plug it in and see if it equals 0. And if it does, that means it's a 0 of the polynomial. And I've allowed that on test when students have done it that way. Now, usually it's a bad sign if that's the way you're doing this problem, because it means you probably aren't going to do well with the other problems where you have to use division to ascertain this characteristic of the polynomial. But on this one, you could get by without using division to see if it's a 0 just by plugging it in. But that's not the way you're supposed to do the problem. So you're supposed to check by using synthetic division. So this will be a 0 of this polynomial if the remainder is 0 when I divide x minus this number into this polynomial. X minus -2 would be x plus 2. The value of c from that would be -2. So essentially, whatever number you're wanting to check is the value for c in your synthetic division. So this would be c. And I'm going to set up synthetic division using -2 as my value for c. So again, my divisor here is x minus c, which is going to be x minus -2, which is x plus 2. So this is what I'm dividing by. But by dividing by this, the value I want to use here in synthetic division is -2. That's my value for c. So it's kind of a circular thing. The number you're starting with ends up being the number that you want to use here in your synthetic division. Across the top, inside the box, you have the coefficients. So 3, 5, -7, and -10. You drop the first number below the box, it's 3. Multiply, you get -6. Add these together, you get -1. Multiply, you get 2. Add these together, you get -5. Multiply, you get 10. Add these together, you get 0. And so the answer is yes. -2 is a 0 of that polynomial. So again, I don't usually write out the rest of it, but that's what I mean, right? -2 is a 0 of w of x. It's a 0 of that polynomial. And for this homework problem, it's just a yes or no question. And there's one of these on the test as well, as I kind of just gave away. And it's really yes or no, but of course, you need to provide work supporting whatever answer you pick. And this is what you're supposed to do. But if you just plugged it in and got it equal to 0 and answered yes based on that, I would go ahead and give that to you also. But that won't work on problems like this, right? If we're trying to determine if x plus 4 is a factor, yes, we want to know if -4 is a 0. It's really kind of the same question, right? We want to figure out if -4 is a 0 to determine if x plus 4 is a factor. But to determine if -4 is a 0, you need to use synthetic division to make that determination, because you need this extra information from that division in order to factor it, in order to get the other zeros. All right, so the last thing we need in order to be able to find all the zeros of a polynomial is some way of determining what numbers to check to see if they are zeros of the polynomial. So think about these previous couple of problems. They suggested that we check -2 to see if it was a 0 of this polynomial. They gave us a number to try, and of course it was just going to be yes or no in this case. But what if they asked us to find all the zeros of this polynomial? And they didn't suggest -2. They just said, you're on your own. You figure out what the zeros are for this. How would we know to guess -2 to see if it was a 0? How are we going to figure out that that's a good number to try here? Same thing on this one, right? We're checking to see if -4 is a 0 of this polynomial, but how would I know to check that number? Or -5 or 3? How do I come up with numbers to check to see if they are factors or zeros of our polynomial? This is what the rational zero theorem does for us. So just to give you an idea of what, and we're going to go back to the rational zero theorem, but this is the kind of problem, this is the ultimate problem that we're trying to be able to do in section 3.2. Here's a polynomial function. Find all the zeros. You're on your own. It doesn't give us any numbers to check. We have to come up with our own numbers to check. So should I guess -2 in this case as a possible answer to this problem? Should I check -2 using synthetic division? Should I check 3? Should I check 4? So I can tell you by just looking at this function that 3 is a complete waste of time. There is no chance that 3 could be a 0 of this polynomial. So I wouldn't waste my time guessing 3 and doing synthetic division with the number 3. 2, however, does have a chance of working, or negative 2. Right, so how would I know negative 2 is actually worthwhile exploring, but 3 is not? You don't want to waste your time on numbers that have no chance of working. Right? This theorem will help us determine what numbers are worth checking and what numbers aren't. It's called the rational zero theorem. If P over Q is a rational zero of the polynomial P of x, now it's kind of weird because you're saying, wait, we're starting off assuming we already have a zero of the polynomial. But here's why we're doing that. Then P must be a factor of the constant coefficient, and Q must be a constant. I put a constant. Oh gosh, forgot. I just covered this in class yesterday, and I caught the typo right away. But now that I'm recording the video, I just completely forget about it. I meant to put factor there. Got my words scrambled up. So P must be a factor of the constant coefficient, and Q must be a factor of the leading coefficient. So if we have a number that is a 0, then these characteristics must be true of that number. The conclusion we draw from that is that only numbers that have these characteristics could possibly be a 0 of our polynomial function, right? So any number that's going to be a 0 has to have a numerator that is a factor of the constant term. So any number that doesn't have a numerator that's a factor of the constant term can't possibly be a 0, because any number that's a 0 would have to have that property. So we're not going to waste our time checking numbers if they don't have these two properties here. The numerator has to be a factor of the constant. The denominator has to be a factor of the leading coefficient. If a number does not have both of those properties, it can't possibly be a 0 of our polynomial. So we shouldn't waste our time on it. Right? So going back to this problem here, our constant term here is 10. Right? So if you think about the factor, well, let's go ahead and list them out. What are the factors of 10? 1 is always a factor of any number. 2 is a factor of 10. 5 is a factor of 10. And 10 itself is a factor of 10. Only numbers with, how do I want to say this? Only numbers with these values in the numerator could possibly be zeros of this polynomial, which is why 3 has no chance of working, because 3 as a fraction would be 3 over 1. The numerator is 3, which is not one of the numbers on this list, and so it can't possibly be a 0 of the polynomial, because any 0 of the polynomial, any rational 0, would have to have a numerator that matches one of these numbers here. So any number that doesn't have a numerator that matches one of these numbers cannot be a 0 and is not worth looking into any further. I can immediately exclude 3 from consideration here because the numerator doesn't match one of these numbers here. But 2 could work, right? Because 2 is like 2 over 1. 2 is a number on this list. And so that numerator does match one of the numbers on this list. So it could possibly still be a 0. It has the right properties to be a 0 of this function. Now, is it actually a 0? We don't know. We have to actually check by using synthetic division, but it has a chance of working. 3 does not have a chance of working. All right. Now, the denominator has to be a factor of the leading coefficient, and that's our fancy term for the coefficient of the highest power of x. So the coefficient of the highest power of x here is 1, right? X to the third power is the highest power. 1 is the coefficient of that. And so what are the factors of 1? Just 1. So another example would be like, let's say 5 halves, right? This has no chance of being a 0 of this polynomial. The numerator's fine. It's a 5. It matches one of the numbers on this list, but the denominator is a 2, and that has to match one of the numbers in this list, and it doesn't. The only numbers that can be zeros to this polynomial have to have denominators of 1. That's the only thing that could work. So if the denominator is anything other than 1, it can't possibly be a 0 of this polynomial. So that's how we will generate a list of guesses for zeros of this polynomial, and then we will have to check those guesses by using synthetic division. But we want to make a list of guesses that have some reasonable chance of working, and the only numbers that have a reasonable chance of working are numbers that fit these properties here. All right. So let's make our list of guesses. All right. So again, I'm talking a lot about the concepts. Let's talk about the practicalities of this problem. So what am I going to have to do to get the answer here? You're going to have to list the factors of the constant term, which we've done here, and I label those as my values of p, right? The numerator, right? P has to be a factor of the constant term. P is the value of the numerator. So let me use a different color here. Right, so P. Q, which is our denominator, has to be a factor of the leading coefficient. So these are my possible values for Q. These are my possible values for P. What you have to do is take every possible combination of a P divided by a Q. Right? And that will be your list of possible zeros that you will then that you will then check by using synthetic division. Right? So I have to take every value of a P divided by every value of a Q. Every possible combination of a P divided by a Q. Now, when Q is just equal to 1, that's the best case scenario. So I'm going to take Q equals 1 as my value for Q. It's the only thing it can equal. And then take every value of P divided by that value of Q. So what I'm going to get is 1 divided by 1, 2 divided by 1, 5 divided by 1, and 10 divided by 1. And that's it. That's every possible combination of a value of P divided by a value of Q. Of course, dividing by 1 just means these just revert back to these original values here, right? So 1 divided by 1 is just 1. 2 divided by 1 is 2, etc. Right? And so we just get 1, 2, 5, and 10 again. As our list of possible values, how do I want to say this? As our list of values that could possibly be zeros to this polynomial. However, notice I'm kind of leaving a space here, and that's for a reason. We don't know, like this listing does not distinguish between positive and negative values, so both are possible. So it's possible that 1 is a 0 of this polynomial. It's also possible that negative 1 is a 0 too. And so we have to consider both the positive and the negatives of these numbers. So really there's 8 numbers for us to consider. Not just 4, but there's 8 because it could either be positive or negative. So these are the only numbers worth guessing as zeros to this polynomial. If it's not on this list, it's not worth looking into. It can't possibly work. These are the only rational zeros. Now, when I say, I keep referencing rational zeros because this list can only help you find zeros that are rational numbers. This list will not help you find imaginary zeros, right? Notice that's nowhere on this list. This list will not help you find square root zeros, right? So if square root of 2 happens to be a 0 of this polynomial, this method will not help you find those kind of zeros, at least not directly, right? So this list only contains the possible rational zeros, which are fractions or whole numbers, right? Okay, so what we have to do next, once we've made this list, is pick a number from the list and then check to see if it actually is a 0 by doing synthetic division. And if the remainder comes out 0, then yes, it's a 0 of the polynomial. If the remainder is not 0, then no, it's not a 0 of the polynomial. So I'm going to pick a number that I'm sure doesn't work just to show you, like, you know, how this process is going to look. Because you're going to pick a number on this list and it may not be a 0. And that means you have to discard it and then check another number. So I'm going to pick 10. Right, I don't know, I'm doing a bad job of picking colors here. Let me pick a different color. So let's do green. Okay, so I'm going to check 10. I want to see if 10 is a 0 of this polynomial. So I will use 10 as my value of C in the synthetic division. I'll put the coefficients of, let's see, what can I do here? Of my polynomial across the top. So I'm going to have 1, 2, negative 13, and 10. I'm going to drop the first number below the box, just like we always do for synthetic division. 1 times 10 is 10. Add these together, I get 12. 12 times 10 is 120. Add these together, I get 107. 107 times 10 is 1,000. Things just got really out of control with this number. 1,007. and 70. When I add those together, I get 1080. That's not 0, so 10 is not a 0 of the polynomial. So 10 doesn't work. We can cross it off our list, but we didn't check negative 10. So I don't want to just completely cross 10 off my list because negative 10 is still a possibility. So maybe what you would do instead is put a plus or minus in front of this, and we can cross out the plus 1. Right? It's still possible that negative 10 could work, because I didn't check that yet, but just to kind of give you a hint on this, normally the most extreme numbers don't work. So like the really big numbers, the really crazy fractions don't tend to actually be the zeros of the polynomial. So I normally would not check 10 first, because I don't want to find wrong ones. I want to find the right one as quick as possible, or one of the right ones. It could be that there's more than one on this list that could work. In fact, there's 3 of them on this list that could work. But I want to find one that works as quickly as possible. Right? So I'm just doing this to kind of show you what doesn't work. Right? If I pick a number, I don't get a remainder of 0. That number doesn't work. I cross it off my list, and I pick a different number from my list. So let's try negative 2. Right? So we'll try negative 2 this time. I'm just picking another number on my list. 1, 2, negative 13, and 10. We'll drop the first number below the box. So it's going to be a 1. 1 times negative 2 is negative 2. We add those together, we get 0. Now that's kind of a weird thing to get, but the process doesn't stop because of that. You just keep going. 0 times negative 2 is 0. Add these together, you get negative 13. Negative 13 times negative 2 is 26. You add these together, you get 36. That's not 0, so negative 2 doesn't work either, right? So I got a second one that was wrong. In fact, and I don't know if you could tell, but I kind of thought negative 2 was one of the right ones, but I was wrong about that. So let's try, I'm pretty sure, I thought it was negative 2, but it must have been positive 2 that works. So let's try 2, right? So I'll have 1, 2, negative 13, and 10. Let's go through the process, hopefully just one last time. 1 times 2 is 2. Add those together, you get 4. 4 times 2 is 8. Add those together, you get negative 5. Negative 5 times 2 is negative 10. Add those together, you get 0. That's what I'm looking for. A remainder of 0, which tells me that 2 is a 0 of the polynomial that we're working with, which also tells me that x minus that number is a factor of the polynomial. So we're looking for the zeros. 2 is one of those zeros. But to find the rest of them, we don't want to go back to doing more synthetic division. There's a couple reasons for that. One is that's not the quickest way to find the rest of the zeros. There's more of them. Yes, they are on our list this time, but we don't know which ones they are, and it could take, we might have to do like 3 or 4 more synthetic divisions before we find all of them. In fact, how would you know you found all of them unless you checked all the numbers? I don't want to have to do 8 different synthetic divisions if I don't have to. So really, the synthetic division process is a method of last resort. We're only doing this because there wasn't an easier way to do the problem. But once you find a 0 of the polynomial, there's an easier path from there. So I don't want to go back to synthetic division when there's an easier path to getting the rest of them, right? The other issue is that there's no guarantee that they're all on this list here. I keep pointing to this for some reason, but it's right here. As I already mentioned, this list will not contain any possible imaginary zeros or any possible square root zeros. So what if one of my zeros was 2i? I'm never going to find it from this synthetic division process. The only way you'll find those imaginary zeros is to do what we're about to do here, which is once you find a number that actually works, you stop and factor the polynomial, just like we did earlier for that one problem where we used the factor theorem, right? One of the factors comes from the 0 that you just found, right? 2 is a 0. That gives me a factor of x minus 2. But the other factor is the quotient from that division. So once you find a 0 that works, stop the synthetic division stuff and start factoring your polynomial. And so this will factor down to x squared plus 4x minus 5. That'll be the other factor, right? And then this we can factor further using the methods that we already learned previously in the course, the easier methods for factoring. So this time we want to find 2 numbers that multiply to negative 5 and add to positive 4. That's going to be positive 5 and negative 1. And then we still have this factor of x minus 2. And then from these factors, we can extract all the rest of the zeros, right? This factor of x minus 2 tells me that 2 is a 0 of the polynomial. This factor of x plus 5 tells me that negative 5 is a 0. I'm sorry, I didn't write that 5 very well. Negative 5 is a 0 of the polynomial. And x minus 1 as a factor tells me that 1 is 0. And that time it just glitched on me for some reason. Tells me that 1 is a 0. All right, and so I have 3 zeros. Now you'll notice negative 5 was on the list, 1 was on the list, but you don't want to just check all the numbers on the list for the reasons I've already outlined. So when you find a number that works, take advantage of that. And take advantage of the information you have from this synthetic division. Stop, factor it, and then use your factors to try to extract the rest of the zeros without doing more synthetic division. All right, let's take a look at another example. Find all of the real and imaginary zeros for the polynomial function. We have f of x equals 24x to the third power plus 40x squared minus 2x minus 12. I can't believe I'm just now noticing this, but there actually is a common factor of 2. I've done this problem so many times and I've never noticed that we could factor out a 2, which would actually make the number of values of p and q would be smaller, right? We'd shrink down the constant and the leading coefficient. We'd have less values for p and q. It'd be a smaller list. But I've never done it that way, and I think I'm just going to stick with just leaving the numbers as is to kind of show you worst case scenario, how bad it could get. And this one's not as bad as it could be because they do have that common factor. A lot of the things are redundant. So let's just get into it. So to make our list of possible zeros for this polynomial that we will then check to see if they are actually zeros by using synthetic division, we have to first identify the values that p can equal and the values that q can equal. The values for p come from the constant term. P has to be a factor of the constant. In this case, the constant is 12, and so the factors of 12 are 1, 2, 3, 4, 6, and 12. Q has to be a value of the leading coefficient. So the possible values of Q are 1, 2, 3, 4, 6, 8, 12, and 24. And that's where things start to get really bad. I guess, both of them can make things bad, but when there's a lot of values of Q, that's kind of the worst one, because that means you're going to have a lot of values and a lot of them will be fractions. So what we need to do is take every possible combination of a P divided by a Q. And this time we have a bunch to consider, not like the last problem. You don't want to do this in a haphazard way. You don't want to say, I'll just take 4 and divide it by 3, and then I'll take 6 and divide it by 2, and then I'll take 1 and divide it by 8. You don't want to be random about it. You need to be methodical about it. And so and there's a couple ways you can be methodical in this circumstance, but the method I always have used is to lock a value of Q in and then run through all the values of P dividing by that particular value of Q. And then that takes care of that particular value of Q. Then you can move on to the next one. So I'll start with 1. We'll take 1 divided by 1, which is 1. 2 divided by 1, which is 2. 3 divided by 1, which is 3. And so you can see what's going to end up happening is we'll get these numbers. The same numbers that P can equal. We'll get all those numbers again. Comma. That takes care of Q equals 1. So these are all the values of P divided by 1. Next, we will have to do the same thing, but with Q equals 2. Take all the values of P divided by 2. So we get 1 divided by 2, which is going to be 1/2. 2 divided by 2 is 1, which we already have on our list, so we don't need to do that. 3 divided by 2 will be 3/2. 4 divided by 2 is 2, which is already on my list. 6 divided by 2 is 3, already on my list. 12 divided by 2 is 6. So the rest of them are values that we already have. So that helps a lot. So Q equals 2 only really added 2 more values to my list. It could have been a lot worse, right? Now we move on to Q equals 3. 1 divided by 3 will be 1/3. 2 divided by 3 will be 2/3. Oops, that didn't write very well. 3 divided by 3 is 1, already on my list. 4 divided by 3 is 4/3. 6 divided by 3 is 2. 12 divided by 3 is 4. So we don't need to write those again. Now let's do q equals 4. I'll just kind of continue on the second line here. So 1 divided by 4, that'll be 1/4. 2 divided by 4 reduces to 1/2, already on my list. 3 divided by 4, that doesn't reduce, so that's a new number. 4 divided by 4 is 1. 6 divided by 4 reduces to 3/2. 12 divided by 4 reduces to 3. And so that's all for 4. Then we move on to 6. We get 1/6. Then we get 2/6, which reduces to 1/3. And if you go through the rest of these numbers, they all reduce. So if you take 3 divided by 6, that reduces to 1/2. So they're already on our list. So for 6, it only adds one more value to our list. Let's do 8. We get 1 divided by 8. 2 divided by 8, which reduces to 1/4. 3/8, that doesn't reduce, so that's a new one. But then the rest of them do reduce, and so they are already somewhere on our list. 12, we get 1/12. The rest reduce, so that takes care of 12. And then 24, we get 1/24. The rest reduce. All right. So here is our list of possible zeros for our polynomial. And the list is twice as big as it might look because we have to consider both the positive and the negative of all of these numbers as possibilities. And so there are a lot of possible zeros to this particular polynomial. So now we need to check by picking a number off the list, running through the synthetic division, seeing if we get a remainder of 0. And if it doesn't work, we can check that number off the list, pick a different number. We just have to keep looking until we find one that works. And this can take a while. So I don't want to take up too much time in the recording by missing a lot of these. And I've done this problem multiple times, even though I never noticed you could factor out a 2 because my mind just wasn't thinking about that. But what I do remember is that it's not a whole number, which is where I would naturally start, right? I don't want to deal with these fractions. Nobody does. So everybody would start with the whole numbers to see if those are zeros. So you would check by doing this. You might check 1 first. You'd have 24, 40, -2, -12. You would check by, going through the synthetic division, but it doesn't work. -1 doesn't work. 2 doesn't work. -2 doesn't work. So that's probably where most people would start. And you might not check the more extreme ones like 6 or 12, but a lot of people probably would go through like 1 through 4. And that's 8 different numbers, right? Because +1, -1, +2, -2. And none of them work. So you might end up doing 8 divisions in this problem and find that none of them give you a remainder of 0. And so you're still searching. And there's still a lot more values to search through. So this is how this process can sometimes unfold. You might do a lot of division, which is why we don't want to use long division. You might say, I don't really like synthetic division. I understand long division better. It's pretty rare, but some students do feel that way. But you don't want to use long division here because that would add so much more time to these problems, right? It's going to be a fraction. And I just did this section yesterday in class, and I'm already drawing a blank about what fraction it is. I think one of them is 2/3. So I want to kind of skip to one that's correct. I want to say -2/3. So let's try that. All right, so let's pick -2/3. That's on our list. We're going to do synthetic division. All right, we're going to have 24, 40, -2, -12. Right. And then we're going to do the synthetic division. And it's with a fraction. And this is the first example I've done where we have a fraction to deal with. But it works out. Let's try that again. 24. So you're going to take 24, multiply it by -2/3. Now, you can use a calculator. That's fine. But you can also mentally work this out. Whenever you're multiplying a whole number to a fraction, especially if it divides nicely, here's an easy process for figuring out the answer. You take 24, divided by the denominator, then multiply it by the numerator. And you can kind of work it out in your head, right? 24 divided by 3 is 8. 8 times -2 is -16. So I write the result underneath the next number inside the box. Add these together, I get 24 again. All right, well, that's nice because I'll get the same answer again, which is -16. Add these together, you get -18. So this time I don't have to think about it. -18 divided by 3 is negative 6, times negative 2 gives me positive 12. And I do indeed get 0 as a remainder, which is what we were looking for, right? So this would not equal 0, right? This is going to be some non-zero number, so that's why we know 1 wouldn't work, 2 wouldn't work, just like on the last example. But once you find a number that gives you a remainder of 0, you stop using synthetic division, for now at least. Occasionally you might have to go back to it, but not on this problem. We shouldn't have to. And then you find the rest of your zeros by factoring. You found 1 so far, right? Negative 2/3 is definitely a 0. But we get the rest of our zeros by factoring. So this being a 0 tells me that x minus that number would be a factor. And it's a weird looking factor because whenever we are factoring, like whenever we've done factoring in the past, you don't usually get factors with fractions. Sorry, I'm having trouble talking. Right. But that's exactly what this one is, if I could write, plus 2/3, right? So it's x minus this number, but minus negative 2/3 gives me the plus 2/3. So if negative 2/3 is a 0, x plus 2/3 would be a factor. And like I said, it's an unusual looking factor, but that's the factor theorem's conclusion, right? So that's how we're going to write our factor. The other factor will be the quotient from this division. So it's going to be 24x squared plus 24x minus 18. That'd be the other factor. And because this other factor is now quadratic, we should be able to factor it further without having to do more synthetic division. Worst case scenario is if you couldn't factor this, you could still find when it's equal to 0 by using the quadratic formula, because that's essentially what we're doing, right? We're trying to find what numbers make this polynomial equal 0. So it's like we're setting it equal to 0 and solving it. And if you want to set this factor equal to 0, you could solve it by using the quadratic formula. So that'd be the worst case scenario for getting the rest of the solutions. However, we're going to go ahead and try to factor it instead of using the quadratic formula. And here, I always think about doing this, factor out the common factor first, right? In this case, the common factor is 6. So we'll factor out a 6. Let's just ignore this factor for now. We already know the answer from that one anyways. Let's just focus on this one here. Factor out the 6. We get 4x squared plus 4x minus 3. Now this one we can't factor by looking for two numbers that multiply to negative 3 and add to 4, because this is not a 1. We either have to do AC method or we have to do trial and error. So I'm going to go do the AC method on this one real quick. So A times C would be 4 times negative 3, which is negative 12. B is equal to positive 4. So I need two numbers that multiply to negative 12 and add to positive 4. And that's going to be 6 and negative 2. I rewrite the middle term using 6 and negative 2. So I rewrite the 4x as 6x minus 2x. The first term copies down, the last term copies down. And then we do factor by grouping now that we have 4 terms here. And we have not just 4 random terms, but 4 carefully selected terms so that factor by grouping should work, right? And so we factor out the common factor in the first group, which is a 2x. That's going to leave me with 2x plus 3. There is no common factor in the second group, but we can factor out a negative. And that will leave me also with 2x plus 3. I don't know why I was writing a 2 there. 2x plus 3. Because these are the same, I can factor it out as a common factor. And that's necessary for factor by grouping to work. If this parentheses doesn't match this one, then factor by grouping does not work. It's a dead end. It doesn't let you factor if these aren't the same. Right? But when they're the same, you can factor them out as a common factor. And what's left over here is 2x minus 1. So now I have this factored. Again, we're trying to find when this is equal to 0. And now that you have it factored, all you have to do is set each factor equal to 0, and then you can solve, right? So we get 2x plus 3 equals 0, 2x minus 1 equals 0. Solve for x in each case. So we get 2x equals negative 3, divide by 2. I'll just keep scrolling down as we need more and more room here. We get x is equal to negative 3/2. That's another 0 of this polynomial, which was on our list. We would have found it eventually if we had kept doing the synthetic division, but you don't want to take that chance because sometimes the rest of the zeros are imaginary or square root type numbers that you will not find on your list, and you don't want to take the chance that the problem you have is one of those. The other 0 is 1/2. And then remember, from way back up here at the top, we also had x equals negative 2/3. That was the 0 that we originally found with the synthetic division. So you want to add that to your list. And this is what you type into Math Excel as your answer. Excuse me. All right, let's take a look at, whoops, okay. I was like, my mouse isn't moving, but it's because, I can't use the pen and the mouse at the same time. They both control the cursor. So, all right, so this is the last example. So we're almost done. I'm sorry, this video is an hour and a half. Now in 3.3, we're going to revisit, it's very closely related to what we're doing now. And we're going to actually revisit this kind of problem in 3.3. But hopefully it'll go a little bit faster since we already laid all the groundwork in this video. So what I'm trying to say is I'm sorry for the length of this video. Hopefully I'll make it up to you in the next video. Try to keep that one a little shorter. So find all the real and imaginary zeros for this polynomial function. This one's going to be a little easier going because the numbers are just a little bit nicer here, right? So the values for p are found from the constant term, which is 30. You don't have to worry about the negative sign. We take care of that by looking at both positive and negative numbers, right? So 30, what are the factors? You might think there's a bunch, but with 30, there's actually not quite. It's not too bad. Not too many. 1, 3, well, I guess maybe there's more than I'm thinking. 5, 6, 10, and 30. It's not too bad, right? There's 6 of them. Okay, so those are the possible values for p, which are the possible values for my numerator. But here's what makes this one a lot easier to deal with. Q can only equal 1. So if I take every possible combination of a p divided by a q, I just get 1 divided by 1, which is 1, 3 divided by 1, which is 3, etc., etc. You get these numbers back, and then that's it. There's nothing else to divide by, so it's just these numbers, both positive and negative. So there's 12 numbers altogether that we need to consider. But as is usually the case, the more extreme numbers are usually not the correct ones. So even though there's 12 here, you can kind of ignore 10 and 30, maybe even 6, because normally the answers are a little bit on the lower end. So maybe it isn't always true, but my experience is like these more extreme numbers normally are not the right ones. So now I actually did not do this problem in class yesterday. I kind of ran out of time. I didn't get this one done. I was planning to do it on Monday, so I don't actually know which one's right here. But I don't know. Now I'm actually thinking about it. I think a problem like this is on the exam, and something I always tell my students for the practice test, because sometimes this number gets crazy. Like 30 is actually a nice, reasonable number. I've seen ones on here like 500 and something, like just really big numbers. And even though q is equal to 1, that's still hard to deal with. And so I like to tell my students, in case that happens on the test, again, it's kind of, I don't like doing this, but usually 1 works on this problem. It's just this particular one. 1 seems to always be one of the answers. So no matter how crazy this number is, just try 1 as one of your zeros. Do synthetic division. You should find that it works. And then from there, you can kind of figure out the rest without having to deal with that really big number. Because I really don't like for it to be that big of a number. I don't want that to be the obstacle. These problems are already hard enough, not having to find the factors of some crazy number that's really hard to figure out. So, all right, so I'm going to try 1. That's my hunch here, right? So positive 1. We're going to have 1, negative 1, negative 29, negative 1, negative 30. Now, what's different about this problem, the reason I have it on the list here, is because it's degree 4, right? I don't know if we've talked about degree yet. I don't think we have, but the highest power is 4. So the previous 2 examples, the highest power was 3. This one, the highest power is 4. So once we find a 0 and we factor it, the quotient we get will be 1 power less. It'll start with 1 power less than the original polynomial started with, which means my quotient will be w to the 3rd power. And so it's not quadratic. And so it's very possible that the factor we get here, because it's not quadratic, we may not be able to factor it using the methods that we already know from before this section. And so we might have to do another round of synthetic division to break it down again to w squared. And once you get it down to w squared, then you can, factor it from there to get the rest of your zeros. Or solve it. If you might not be able to, in fact, I think in this case, it won't be factorable, but we will be able to actually get our solutions once we have it down to the quadratic level, right? And so let's go ahead and start the process here. So we have, drop the 1. 1 times 1 is 1. Like I said, don't let this bother you. You add these together, you get 0, which seems a little weird to me, but maybe this works out still. 0 times 1 is going to be 0. Add that together, you get negative 29. Negative 29 times 1 is negative 29. You add that together, you get negative 30. Negative 30 times 1, oh, my hunch was wrong. I get negative. So this is not the problem that shows up on the test, because the one that's on the test, 1 always works. And here we have to be careful, because it almost works, and we might trick ourselves into thinking it cancels out. We might accidentally think, oh, okay, that's positive 30, because we want them to cancel out, and the numbers are the same, but it's negative 30, right? Negative 30 times 1 is still negative 30. And when you add these together, you get negative 60. And so I am mistaken. 1 doesn't work. Let's try negative 1. I'm really lost. I'm lost on this problem. I mean, this is how I'm experiencing this problem now, not really knowing, because the other problems I kind of knew what was going to work. But this one I really forgot. I really don't remember which number works. So this is the position you're going to find yourself in. You'll have this list of numbers and you have no idea what the right one is going to be. And so you just have to keep checking. So I'm just going to check negative 1. That seems easy enough. 1, negative 1, negative 29, negative 1, negative 30. I'm getting this weird feeling that maybe, no, it can't be a typo. I was going to say maybe I have a typo here. That has happened to me in the past, but I copied this problem from Math Excel, so it should be valid. So that can't be it either. Okay, so we should be able to find something. If there's a typo, it's possible that none of the zeros are rational, and you just won't find any that work with synthetic division. But it's from Math Excel, so it should work. 1 times negative 1 is negative 1. Add those together, you get negative 2. Negative 2 times negative 1 is positive 2. Add those together, you get negative 27. Negative 27 times 1 is positive 27. You add those together, you get 26, which is, we're getting better results, but not really actually, because this is going to be negative 26. It's still going to be a big number. So sorry, it's not even better. It's negative 56. Doesn't even matter what it is. If it's not 0, it's not good. So 1 and negative 1 both do not work. So I can just cross it off my list. Let's try 3. So we'll have 1, negative 1, negative 29, negative 1. If this one doesn't work, because again, I feel bad, the video is already an hour and a half. I might be able to cut it down a few minutes by cutting some things out, but it's a pretty long video. If this one doesn't work, I'll just pause my recording and maybe ask you to pause the video. In fact, why don't we just do that now? Let's pause the video. I'm going to pause my recording. You pause the video and help me find a number that works. So why don't you try doing synthetic division with the numbers we have left on our list and see if you can find one that works. And I don't know, maybe we'll find the same one. If not, we might find 2 different ones that work, and that's fine either way. But see if you can find one that gives you a remainder of 0. And I'll do the same, and I'll just resume once I have something that works. Okay, so I was starting to despair there a little bit. I thought maybe I made a mistake. I don't know. I couldn't figure out what was going on. And I'm surprised. The first result we can find is such a big number, I guess. I was expecting like 1, 2, or 3 to work. By the way, you might say 2. What do you mean by 2? I did not catch that one. Maybe you caught that earlier. But as I was kind of looking at why am I not finding something that works, I look back up here to just revisit the work I did earlier to see if I made a mistake. And I noticed I left 2 and 15 out. Those are other factors of 30, and that's very dangerous. It could very easily happen that the one you accidentally leave out is the one you need in order to get the 0 of the polynomial. So I thought maybe that's what happened is, oh, I forgot 2. That's probably one of the answers. And I was still like, wow, 2 and negative 2 don't work either. And so ended up checking 7 numbers before I finally found one that worked, right? And it was negative 5, right? So you can see all the work I did here. Finally, I find a number that gives me a remainder of 0. So that can happen. I did 8 synthetic divisions. And on the 8th one, I found a number that worked, right? So I can stop and factor. And so I'm going to stop and factor. One of my factors will be x plus 5, right? It's minus negative 5. The other factor will be the quotient here, which is x to the third power minus 6x squared plus 1x minus 6. Now this one you can actually solve by factor by grouping. And so that's pretty common for a lot of these problems, but it isn't guaranteed. So if your factor is still x to the third power, there's always the possibility that you would have to do more synthetic division if you couldn't factor this to break it down again. The nice thing about that is you don't have to redo the p's and q's unless you think that would be helpful. You can keep using the same list you've already established with the original problem, and you can still leave crossed out the things you crossed out already, which we crossed out a bunch of things, right? And so, because if it didn't work in the original polynomial, it's not going to work in this new one, because if it's going to work here, it should have worked in the original one, right? And so I still know 1 doesn't work. I still know 2 doesn't work. I still know 3 doesn't work in this one because it didn't work in the original one. So I just use the same list, leave the same numbers crossed out, and do more synthetic division. So I want to go down that path just to show you, again, worst case scenario, in case you can't factor this by grouping, what you would have to do in that case, which is do more synthetic division, but not on the original polynomial, but on this new factor that you just created. So I'm going to do some more synthetic division with this expression here, right? It's going to be 1, negative 6, 1, negative 6. And just based on how that looks, I can tell that 6 is going to work, which is the next number in our list anyway. So probably would have been the one we would have checked no matter what. So let's check 6, because again, we already checked 1, 2, 3, and 5. So 6 would be the next number in our list to check. And so we'll drop the 1 below the box. 1 times 6 is 6. We get 0 here. 0 times 6 is 0. Add those, you get 1. 1 times 6 is 6. Add those together, you get 0. So we get another remainder of 0. And so we stop and factor again. One of my factors here will be x minus that number, so x minus 6. The other factor is this quotient, which is going to be 1 power less than what this started with. So it's going to start with 1x squared, 0 x's, and then plus 1. Right. And so that's how this one breaks down. This breaks down as x minus 6 times x squared plus 1, which is what you would have gotten if you had done this by factor by grouping. Right. So it's something to look into, because like I said, the problem that's on the test, that's kind of like this one, where 1 always works. It also happens to be the case that once you use 1 and factor it down, this result can be factored further by factor by grouping. But I wanted to show you what you would have to do if factor by grouping wasn't an option, or if you're just not sure how to do factor by grouping, this would be the other way you'd have to go about doing it. And you break it down like this. Now you finally have it down to quadratic, right? It's finally down to x squared. And so from there, you should be able to factor it further without having to do any more synthetic division, p's and q's, any of that stuff. But this isn't factorable, so we just have to solve it as is. So again, imagine we're setting it equal to 0 because we're trying to find when does this polynomial equal 0. So imagine setting this equal to 0. And then each factor gets set equal to 0, right? So we get x plus 5 equals 0. We get x minus 6 equals 0. And we get x squared plus 1 equals 0. And then you solve for x in each case. In these two cases, you get the answers that we already found by synthetic division, right? You get x equals negative 5. We already knew that one. That was the first one we found. We add 6 to both sides. We get x equals 6. That's the second answer we found. But we're going to get some more answers from this factor. Solve it for x. It's quadratic, but there's only one x in the equation. So you can just get x by itself. Subtract 1 to the other side. You get x squared equals negative 1. You take the square root of both sides to solve that for x. And so you get x equals plus or minus, because you did the square root to both sides. The square root of negative 1 is I. It's imaginary. So you would never have found these zeros if all you did was synthetic division. Even with the entire list of numbers that we had, you would only ever find these two. You would never be aware of these two over here, the plus I and the negative I. And so that's why it's important that when we find a 0, we stop and factor and try to break it down so that we can find these imaginary zeros or these square root zeros that might exist. All right, So that concludes the video on section 3.2. I apologize for the length of the video. I will see you in the next video for section 3.3.